Hello everyone, welcome to another EMS webinar. Our topic for today is simulation of resistance heating devices in EMS. Before we start, let's have a look at our agenda for today. I suppose that some of you might not be fully familiar with EMS, so we're going to start by a brief overview of EMS and its solvers. Then we're going to see what is the conduction heating or the resistance heating used for in the industry, and we're going to have a quick look at the physics behind this engineering method. Then finally we're going to show you how you can set up your resistance heating application or simulation in EMS, and how you can generate those important results for this application. We're going to wrap up this webinar by a question and answer session. So if at any point during my talk you have a question, feel free to type it in the chat box, and I'll do my best to answer it at the end. So EMS is an electromagnetic simulation software, and it has 6 basic solver types, and these six solvers can be loosely split into 2 groups. The first group is electric solvers. It contains electrostatic, electric conduction, and AC electric module, and these modules allow you to perform simulation of electric fields, compute capacitances, dielectric breakdowns, and these solvers are mostly used in simulation of bus bars, transmission lines, fuse designs, any application where the physics behind it is driven by the electric field or a current distribution. In these cases, you would use one of these electric solvers. Then we also have magnetic solvers. There are also 3: magnetostatic, AC magnetic, transient magnetic. They allow you to compute magnetic fields, forces, torques, inductances, and all the associated phenomena in different domains. For example, magnetostatic works in a steady state domain, AC magnetic works in a frequency domain, and transient magnetic allows you to work in a time domain and get fully dynamic results. EMS electromagnetic solvers coupled with some other physics solvers as well. EMS has its own thermal and structural simulation packages, which can be directly coupled with its electromagnetic solvers, and then you can get a fully multi-physics, multi-domain solution. EMS also couples with the SolidWorks Motion, which allows you to perform fully dynamic electromechanical simulations and get a transient response of different mechanical systems. So some of the most important applications of resistance heating method are stress relieving, annealing, and forging. You would use you would apply resistance heating on a specimen, on a workpiece to rise up its temperature and make it suitable for further machining and further use. Heat treatment for stress relieving and annealing is usually conducted conducted basically in order to realign the metal crystals and make the workpiece less prone to cracking or splitting. It is conducted at lower temperatures, typically between 200 and 700 Celsius. On the other hand, forging demands that you make the workpiece much more make it easier to that you make it easy to mold and form. So in that case, you will have to increase the temperature of it to a much higher zone of probably over 1000 Celsius. So automatically we can see what kind of results would be important and what kind of performance parameters will be important in this kind of application. Obviously, you need to know how much time does it get to reach certain temperature, what is the efficiency of the process, and how evenly the temperature is distributed inside the workpiece. Sometimes it is your goal actually would be to have an uneven temperature distribution. Sometimes you want to have it as even as possible, depending on what you want to do with and what kind of forming and shaping you want to apply the workpiece on after the heating. The example we're going to be working on today is basically a steel bar held by a set of copper contacts on both ends. These contacts are supplying a current to the workpiece and producing losses which lead to the temperature rise. So what we basically have is current coming in at one end and leaving the workpiece on the other end, and this current is generating the losses in the workpiece that lead to the temperature rise and are eventually making this workpiece prone to forming and forging and whatever you want to do with it. The AC current is most frequently used for resistance heating in the industry, and this leads to a non-uniform current distribution in the workpiece due to the skin effect. So as we all know, the incident current produces the changing magnetic field. This field produces eddy currents in the material, and these eddy currents are oriented in such a way that they partially cancel the incident current, and mostly on the interior of the conductor. So therefore, most of the current will be in the skin zone or in the exterior zone of the conductor. And the depth at which current is going to, how much is this current concentration going to be pronounced depends on a few different factors. Of course, the frequency, the higher the frequency is, the thinner this penetration depth is going to be. Also, the permeability of the material has its own effects, as well as the resistance. But at any rate, we can, before running the simulation, we can usually estimate for a given frequency and conductivity of material and permeability of the material. We can estimate this skin depth and then apply a finer mesh in this zone at which we expect to get most of the current to get higher accuracy of our results. Another phenomena that makes this simulation a bit complicated is the fact that the material conductivity depends on the temperature. So basically, we're trying to compute a temperature rise in the workpiece, which is an electromagnetic system. But at the same time, properties of this electromagnetic system depend on the temperature. And this is why it is very important and very useful that EMS allows us to easily and seamlessly couple the electromagnetic and thermal solvers so that we can get a truly accurate and useful solution. So now that we sort of understand the complexity of this problem and what is going on, the best thing would be to go directly into SolidWorks and have a look at the model the assembly I have just described you. So this is basically one steel bar held in place by a set of copper contacts on both ends, and these contacts are supplying the current to it. This assembly, in addition to the contacts and the bar, also contains an air domain whose purpose is to enable field lines to distribute in the ambient around our assembly. So now, if we click at the EMS Manager tab, we move to the EMS environment, as you can see right inside SolidWorks. Excuse me. The way you start any EMS simulation is by right-clicking at the name of the assembly, selecting Study, and then choosing the appropriate solver which you want to use. As you can see, all 6 solvers which I have described are contained here. You can also specify the coupling analysis that you want to do. In our case, we have selected AC magnetic study because we want to do a simulation with an AC current. We have defined its frequency, and we have also checked this thermal coupling and the transient option as well, so that we can see how much time does it take for the workpiece to reach certain temperatures. The first thing when defining your, this is now the second actually thing that you need to do when defining a simulation, is specify material for each part. As you can see, all these contacts are made out of copper. Other than and also we have an air as material for the ambient. But the most important part, and the part where we'll focus most of our attention, is this bar, which has been defined as a mild steel. To do that, you right-click at the name of the part, and then you select Apply Material. And then you get to see this EMS library, material library, in which under the ferromagnetics you can find the mild steel which has been applied to the bar. But to make sure that EMS computes the eddy currents in the bar and account for the skin effect, which is the result of those eddy currents, you need to right-click at the bar and select Turn on Eddy Effects. And finally, let me show you how you can specify the conductivity dependence of for the bar material versus temperature. So to do that, you have to select one of the bodies that form this part and right-click on it and select Edit Material. And then here you have all the options that are defining the material properties of your part. First of them is conductivity, and as you can see here, we have few different types of conductivity: isotropic, orthotropic, which means anisotropic. And what interests us the most today is this isotropic temperature dependent. So once you select that, you can left-click here and to the curve database, and you can select some of the predefined curves that you have from your previous work, or define a new curve by entering relevant points on the conductivity versus temperature table, and you can define easily this curve for yourself on the range of temperatures that interest you the most. As you can see here, this bar has been it is a one SolidWorks part, but it consists out of two bodies. One of these two bodies is just basically a thin layer at the external edges of the bar, and the reason why we have split this bar into two bodies is so that we can apply, when defining a mesh, so that we can apply a finer mesh control on this external part of the bar. As you can see here, we have selected in this mesh control window, we have under bodies and components, we have selected only this external component of the bar, and we have defined the maximum mesh element size on this component, and this is going to eventually lead to a finer mesh quality in this zone where we expect to get most of our current, and which is most important to get accurate results. Another thing we need to do is define the current loading on this in this assembly. So since all of the parts are actually all of these parts in our assembly actually participate in the current flow, we have selected all of them, and by right-clicking at coils, we have applied a solid coil. And as you can see, this solid coil feature includes all of these parts, and it defines, in addition to that, it defines the entry and exit port to this current flow. The way to do that is you simply have to select all the faces at which current is entering your system, and also all the faces at which current is leaving your system, and assign them properly. If you go to the General Properties tab, you can here define the current magnitude and its phase, or if you wanted to have a voltage-driven system instead of a current-driven system, you can also do that by selecting the voltage-driven coil. So now that we have defined the material and the eddy currents on the bar, as well as the conductivity dependence on temperature, and that we have defined the current loading, we can move to this thermal input folder and define the thermal interaction that takes place between our assembly, which is the heat generation component of the system, and the ambient, which has some certain constant temperature and is receiving the heat emitted from the assembly. And the way to do that is to right-click on the temperature inputs and select convection. In the convection properties window, you need to select the ambient, which is in this case air, and define its coefficient, convection coefficient, which is for air usually about 10 watts per Kelvin meter squared. You also need to define the temperature of that ambient, and then you're pretty much good to go. We have defined all the electromagnetic parameters, we have defined all the thermal physics going on, and we have defined the mesh control on the external edges of the bar. So now we can go to the results folder and have a look at what kind of results EMS is able to give us for this kind of problem. So maybe one of the most important results are, in this case, contained in the thermal results folder, which is all the way at the bottom of the EMS tree, where you can find the temperature folder. Double click on the default plot, and it is showing us the temperature in Celsius for a specific time step in our simulation. So let's right click on this plot, select edit definition, and here we can see that this is actually for the third time step, which is after the 2 minutes from the beginning of the simulation. If we move this slider to the right, we can see how the temperature is increasing. If we go all the way to the end, which is 10 minutes, we can see that the hot spots of the bar reach temperature of about 1300 Celsius. If you unselect this show plots on the selected entities, EMS is going to give you the plot of the temperature rise on the whole assembly, including the contacts. If what interests you is also if you want to see a 2D plot showing you the temperature at a specific point versus time, the way to do that is right-click at the temperature folder, select 2D plot, linear, and then select any point at which you want to plot these results, and then select plot all time steps. Hit OK, and EMS is showing you how does the temperature of this point changes versus time. You see that it's reaching almost, actually about 1500 degrees Kelvin this time. You can plot results either in kelvins or in Celsius. As I've mentioned, a parameter which is quite important is how uniform the temperature distribution is in the bar, in the workpiece in general. To see how evenly the temperature is distributed on the cross section plane of the bar, you could maybe right-click on this temperature plot we had, and then select clipping, and then select section clipping, and then select what plane, which one of these SolidWorks planes you want to use to cut this assembly and view results. So we have selected this right plane, and EMS is allowing us to have a look at the inside of the bar and see what is the temperature distribution over there. We can also plot the temperature distribution on a line that connects two reference points that we have defined. That's why before running the simulation, we have defined two reference points in this assembly, one at each side of the bar, as you can see, point 1 and point 2. So to do that, you go to the temperature folder, right-click on it, and select 2D plot, linear, and then this time we will select import points. So EMS is able to import those SolidWorks reference points that we have defined before running the simulation. We define how many steps or how many points between those two endpoints we want to have in our plot, and we select for which time step, let's go all the way to the end, we want to plot the temperature distribution. Hit OK, and as you can see, the temperature distribution along the cross section of the bar is pretty even between these along the width of the bar. It only drops from 1500 at the edges till 1450, which is not too much. I mean, considering that all of the currents and all of the losses are concentrated in the external sides or external regions of the bar. To see what does the current density distribution look like and how much this skin effect is actually pronounced, we can go to the current density plot and have a look at one plot that I have predefined before this webinar, and we can see the current density distribution on a cross-section plane of the bar, and you can clearly see how strongly concentrated it is in the external regions of the bar. We can also plot the current density distribution between those 2 points that we have just used in a temperature plot, and see how rapidly the current density drops, it's quite exponential, as expected, drop in the current magnitude as you move along from the edges towards the external regions of the bar, and it then on the other side it picks up again. So as you have seen, EMS allowed us to pretty quickly and pretty seamlessly integrate one temperature-dependent electromagnetic simulation and obtain results such as current density distribution, temperature rise, and temperature distribution inside the workpiece for a range of time steps without having to go through coupling of different softwares or different packages. It was pretty much just one. It was just a unique solution to this problem, which we have been able to achieve with EMS. Although it required a fully dynamic integration between the electromagnetic and thermal solvers, as you've seen, it's pretty straightforward to work on it, even if you are not an expert in a thermal or some CFD simulation with EMS. It's quite straightforward to set it up. So with this, I would like to end this talk from my side, and invite you to have a look at our website and check out some other videos that we have on our YouTube channel. If you would like to have a trial of EMS yourself, you can get in touch with us at this email address or at this phone number. If at this point you have had any questions, it would be my pleasure to answer them. And now would be actually the right time to type in any questions if you haven't done it yet. Okay, seems like we have no questions for the moment, but if you come up with something, use these contacts to get in touch with us. I would like to thank you for joining us today, and I'm looking forward to another webinar that we will do together soon. Thank you, and bye-bye.